Hi. Time for exam 3. Let's see. It's on chapter 4. I would say 10 problems. And need to be able to differentiate. Which is technically chapter 3. We're talking basic and product rule and chain rule, right? So basic, product, chain. I'm just gonna say right now, we'll say later. Let's go with min-max problem. Now, this is, you have two types, right? You have the boring one from 4.1, and then you have also the word problems for optimization. They're also min-max problems. So, two flavors. This is vanilla. We'll deal with the chocolate later. Mean value theorem. So, formula and calculation. Then we have first derivative test plus conclusion. That means increase, decrease, min-max. Second derivative test plus conclusion, which is concave up, concave down. Graphing functions. Everything is given. So you need to look at the stuff. Remember how that was a very long problem which contained mean and max and first and second derivative and x-intercepts, asymptotes. So all of that stuff will be given to you because you will have individual problems. Yes? Well, you have to calculate. That's understood. Just like critical points are understood for the first derivative test. So yes, inflection points will be the part that you will have to compute because that's where the concavity changes. That's how you know where to start or end the interval. Graphing functions. Linear approximation. Tangent line. Or formula. So maybe you memorize the formula, the one line tangent line problem, or you know the entire procedure for tangent line and you just go and grind through the entire thing. Skip over there. There's a L'Hopital's rule. And we have 0 over 0. Infinity over infinity, 0 times infinity, and then the exponential stuff. Finally, antiderivatives. Antiderivatives That's the plus C business. And as a sub-problem,
I assume nothing will be required from 4.8 Newton's method.
so know the way to calculate C. And finally, word problems. We have three flavors. Number one, optimization, which is the min-max stuff. Differentials, and going back to related rates. That was 3.11 as a contrast and preparation, obviously, for the final two optimization. Now, the key in differentiating between the two is the related rates have the wording of how fast is something changing. So related rates, how fast is changing in time. Okay, I'll put that as well. Find the rate of change of, there we go. So optimization problems are the ones that have two equations.
Which is treated like variables.
And then you plug in.
Problem, we can divide it to the other side of the equation.
Yeah, that's it. Yes.
That's part of the value theorem, right?
Other than like villains, like you know how we have to say like the definition.
Yeah, it's perfect for mean value theorem, for formulas for integration, for procedure for, let's say, exponential, for L'Hopital's rule or L'Hopital's rule itself. There are a few good, right, opportunities to grab those free points. Any questions, concerns, problems? Yes.
I mean, the method of going through the first and second derivative tests. I think I took some notes in my notebook here.
Yeah, what's the problem?
I don't have a specific problem. Moment, please.
Yep, get it.
Very well.
Why is it a secret?
Sorry.
Working on labs that you prohibited.
No, we can't. That's graded. Okay. You can get it either on the homework or in a textbook.
Can we do an example of the graphical functions?
Mm-hmm.
So y equals 3 root x minus x to the 3 halves.
Wonderful. All right, so let's start with this. Please get the problem for. Actually, there will be a first and second derivative test inside of this problem.
Okay. That's good to me.
So yeah, so you got lucky. You don't have to look for one now. Ready? The question is graph. Now, I said to you that everything will be provided for the graph question, but each individual part of this could be a standalone problem for the test, because the first and second derivative and min and max are within this problem. So we have to calculate everything. Anyway, So x and y intercept would be 0, 0, and a domain 0 to infinity, because we can't plug negative numbers under the root. We can't plug 0, therefore it has a bracket. So 0 is okay, and we also see that at 0, 0 you actually have the y-intercept and x-intercept at the same time. Now, yes? Yes. But for the x-intercept when y is equal to 0, I think we also have a 3, so I have to compute it. There might be another x-intercept. So 3 root x minus root x cubed equal to 0. When I factor out root x, I get 3 minus x equals 0, so x equals 3. So we do have another x-intercept. So one is at 0, 0, one is at 3, 0, and then we also have 0, 0 for the y-intercept. Nova hasa, because the roots, radical functions, do not have asymptotes. Log functions have asymptotes, rational functions have asymptotes. Exponential function has an horizontal asymptote. But not for radical functions, not for polynomials. And then sine and cosine, no asymptotes. The others do have asymptotes. So you have to be kind of careful which ones have them, which ones don't have them. And at this point, we are going to look for the first derivative test. So first derivative first. This is 3 divided by 2 root x minus, what else? So that's 3 to a half, so it's 3 halves x to the, well, square root of x to the half. So that's our first derivative. I will box it so we can find it later. And for the first derivative test, I need to set this equal to 0. Now I can divide both sides by 3 halves, so this becomes 1 over root x minus root x equal to 0. And the answer is clearly 1, right? If you move root x to the other side, and then you cross multiply, root x squared is just x, so x equals 1, and that's your critical number. So in order for you to calculate first derivative test, you first have to find critical points, critical numbers, and in this case we have 1. So here is the first derivative test now. Partition is done on vertical asymptotes and critical numbers. We do not have any vertical asymptotes, we only have one critical number. So my partition will start at 0, and here is 1, and then it goes on to infinity, right? So this is my domain, and I see that I have a partition here, so I need to pick 2 test points. Now I have square root of x, so easy test points would be a quarter, because I can take even square root of that. And number 4 is also good, because I can take a nice square root of that. So those are my test points. So the red one are test points. So you take the first derivative, set it equal to 0 to find critical points. You use critical points and vertical asymptotes to partition the domain. And then in each of the partitions, you pick a number, which is called a test point, which you are going to plug into your first derivative test. So first derivative test of 1/4 is going to be 3 divided by 2 times square root of 1/4 plus 3/2 square root of 1/4. And we are looking for this number to be either larger or smaller than 0. That's what I said. Please pay attention. Thank you. So now, 2 1/4 square root of 1/4 cancels because square root of 1/4 is 1/2, and that cancels the 2. So I have 3 minus 3/4, which is larger than 0. We don't care how much it is larger than 0. So we have an increase on this side. So f of x increasing because it was first derivative was larger than 0. Now the first derivative at 4 is 3 over 2 root 4 plus 3/2 root 4. So in this case, that's what I said. Oh my God! Did anyone listen? So this is now 3/4 minus 3, which is less than 0, which in our definition is a decrease. So we have increase followed by the decrease, which means what do we have at our critical number? We have a max. Because you can see the trend, right? It looks like there will be a max there. Great. So we found, oh, I did not compute the y value for this x. So when I plug in 1, I just get 3 minus 1, which is 2. Okay. So, yep, f of 1. Every time you need a y value, you have to use the original equation, because original equation is y equals f of x. First derivative is y prime, but your points are not x comma y prime. Your points are x comma y. So every time when you have to calculate any of the points on the original graph, you always, that goes for min, max, inflection, any of the intercept points, any point you ever have to compute, you always have to plug that in the original equation, because the points are always x comma y, and original equation is y equals function. Test points, which are the red ones, are placed into the first derivative test and later second derivative test to find just whether it's smaller or larger, so we can comment on that. So we have a max at 1, 2. Great. Second derivative test is exactly the same procedure like the first derivative test, except we work off of the second derivative. So now we have to take the derivative of our derivative from before. Our derivative from before was 3/2. So first derivative written in the easy way. So this is writing the first derivative easy way for second derivative calculation. So when we subtract 1, this is 3/2, and then negative 1/2 x to the negative 3/2 minus 3/2, and then 1/2, and then x to the negative 1/2. So for the derivative, you drop the power, and then you subtract 1 from it. So it should be. So now the second derivative is negative 3/4 x to the negative 3/2 minus 3/4 x to the negative 1/2. So that's our second derivative. we set that puppy equal to 0 to calculate inflection points. In a second derivative we have inflection points. So negative 3/4 I can write this as 1 over square root of x cubed minus 1 over square root of x. It will help if I write it this way, because anytime we're solving equations, factoring is our friend, the best friend, better than a dog, because dogs can't help too much when doing second derivative test, right? Right. Well, they do help. They eat your homework, and then you come to school and say, "Dog ate my homework." Still 0. So now, when you have this negative 3/4 equal to 0, that has no solution, so that just drops. You kick 1 over root x out, and what's left is 1 over x minus 1 equal to 0. So 1 over root x equals 0 has no solution, because when you cross multiply you get 1 equal to 0. Yeah, right? Now the second one does have a solution, which is 1 over x minus 1 equal to 0. That's 1 over x equals to 1, and x equals 1. Now that makes no sense.
Can you go back to when you pulled out the 1 over root x?
I can.
Like, so you divide by 3/4, so then you have the 1 over root x cubed minus 1 over root x. So you pull the 1 over root x out. Oh, and then it'll be x squared. Okay.
Yeah.
That makes sense.
So it's a plus now. Thank you. I'm trying to figure out what's wrong, because I got the garbage answer. There we go, much better. X is negative 1, and we throw that in the garbage because it's not in domain. There we go. Not in the domain. Well, you just saved my life, because I was about to go nuclear. Because you can't have inflection point and the maximum at the same value. It's physically impossible. They're completely opposite concepts, right? If you have a maximum and then you have inflection point, you see that one side of the graph will not match. It's impossible to have both. Right, inflection point and critical point at the same. Its inflection point always wins if they happen to be at the same value. All right, so now we can do the second derivative test. We partition again at 0. We have no inflection points that we can use, so the entire partition is just one partition. Right? One piece. No vertical asymptotes, no inflection points, so entire domain is just one partition. Pick any point, and clearly number 1 is the nicest in this case to pick as a test point, because we have square root of x, so square root of 1 is just 1. So now to do the second derivative test at 1, we have our second derivative test, which is negative 3/4 times 1 over square root of 1 cubed plus 1 over square root of 1. That's negative 3/4, 1 plus 1, and the whole thing is negative. We don't care what the value is, and as we expect it to be, is concave down. Why we are expecting it to be concave down before we even calculated anything? Because we have a maximum. Concave down piece must have a max. Concave up piece has a min. So we already knew the answer, and we just did the whole calculation to confirm it. So everything matches. Yes, you look like a Statue of Liberty for a second right there. Yeah.
Really? I just realized that. For the exam, when we used to graph something, do we need to like go through tests if we know exactly what it's going to look like?
As I said in the first introductory part, there will be one problem on first derivative test. That means whatever you see right here on the screen, starting from the first derivative all the way through this, plus writing the answer from 3 to 7, function is decreasing, from 7 to 9 is increasing, right? That is considered the first derivative test full problem, right? What I said, first derivative test plus conclusion, right? That's what I said in the intro. And for the second derivative test, the same spiel. You do the second derivative test. Now, those two problems will not be linked at all. One will be polynomial, the other one will be whatever. So when it says do the second derivative test, please don't do first derivative test as well, because no one is asking you. You have to get the first derivative to get to second derivative, but there is no need to do the test, right? So one problem for first derivative only, one problem for second derivative test only, right? Now for the graphing problem, all of this stuff will be given. And you just draw the graph looking at the specs. So now we have everything, right? And I can draw. I know that there is nothing left of a y-axis, so I'm not going to focus too much on drawing left. I do have 0, 0 as a point of interest. I believe we had 1, 2 to be our max. Now, whenever you have a max point, you immediately draw a little frown, okay? So draw a little frown through max. We are going to have another x-intercept at 3. And that's it. So now we're just going to go up, hit the maximum, and shoot down through 3, and just leave it fall. And you see that it's concave down because it opens down. It starts at 0, 0 because there is no domain to the left because of the square root. The maximum point is at 1, 2. You should label that as 1, 2, so it's clear. X and Y axis are labeled for half a point each. So there's a point right there. And
I see there's an even function. Either, is it?
It's not an even function. Even function has to be symmetric on the y-axis. This one has nothing on the other side of the y-axis. You would have to have another piece like this in order for it to be even. So
what I meant to say was if the maximum was on the y-axis, it still wouldn't be symmetrical because one side would be.
no, this is 1 unit, this is 2 units. So
That's the good point to make.
So this was actually the good question, right? Where you have the first derivative test and second derivative test worked out completely, including the way to graph the function, right? And I also mentioned about your asymptotes, where we said that the first asymptote, the vertical, horizontal, and slant asymptotes do not appear at all for radical and polynomial functions and sine and cosine, but then the other ones will have something. Any other questions, concerns, problems? Yes?
So if we were given an area problem that asks to find the minimum area that would be used to construct something, or that we're asked to find the minimum area, Could we then find that through the second derivative test, basically, or to confirm that it's a minimum through the second derivative test?
Yes.
Concave up, and that would be a minimum.
Very good. You can do that. Yes.
I do have one problem here. One of the exams, if I'm finding derivative of 2x to the negative third over x squared minus, no, it must be 2x minus 3 over x squared minus 1.
Hold on, I have to write that. So what is the? Actually, I'm going to look at it. It's easier.
I was supposed to graph the function. So, play them here. Okay, similar to what we did here.
X squared minus 1.
Yes. There's a better problem. I just want to go ahead and use that instead.
So this is the one which is called rational function, where you have division of two polynomials, and this is the one that might have some asymptotes, right? Well, we start with domain, and in this case domain is, well, we see that we have issue at 1 and negative 1. So domain is negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. So we have two interruptions in the domain. For x-intercept, we set y equal to 0. If y is equal to 0, that means 2x minus 3 is equal to 0, from where x is 3/2. So 3/2, 0 for x-intercept, and for y-intercept, x is equal to 0, so that's going to be negative 3 over negative 1, which is 3, so 0, 3. So this is algebra, right, when you get these. Next is to get those asymptotes. So we have vertical asymptotes at x equals negative 1 and x equals to 1, because those are the two interruptions in the domain where denominator is equal to 0. Now, anytime you're working with asymptotes, if you are not sure, well, you have those limit definitions of asymptotes that you can unleash upon the problem to verify. Horizontal asymptote, you can use the definition, which is the limit goes to infinity, or if you know the rules from your pre-calculus course, because these are polynomials, when the denominator has higher exponent, horizontal asymptote is at 0. So y equals 0 for horizontal asymptote. Now, if you have horizontal asymptote, immediately means no slant asymptote, also known as oblique asymptote, because you can't have both at the same time, one or the other. It's time for the first derivative of our function. Now our function was what? 2x
minus 3 over x squared minus 1.
2x minus 3 over x squared minus 1.
I just use quotient rule for this.
Exactly. I'm going to use my math button. So 2x minus 3, differentiate. It's a little bit faster than the quotient rule. So 2 negative x squared plus 3x minus 1 divided by x squared minus 1, everything squared. And now we set that equal to 0. And when you set this equal to 0, the denominator dies, the 2 dies, so the only thing you have to worry about is negative x squared plus 3x minus 1 equal to 0. Now, you would, well, you know what? I'm going to actually, for the derivative, pull negative 2 and change all the signs. It's better.
Yeah, get rid of the negative as well.
Yeah, I took the negative out. It's better. All right, so now this cannot be factored because it would be factored in the derivative.
Yes.
So let me see if the equation solver would do a good job. Solve for x. Oh, perfect. So when you solve this, you get x equals 3 plus minus root 5 over 2. So we have two critical numbers.
Oh, yes.
So now we have two critical numbers, and all I want to know is this number 3 plus root or minus root 5 bigger or smaller than 1. Because when I do partitioning now, I have to already split at negative 1 and positive 1. Those are vertical asymptotes. And here I'll have 4 lines to put. I just need to know which order I need to put them in. So I actually need decimals for these values. So now root 5, so 3 plus root 5 over 2. Root 5 is about 2.23. So this is about 5.23 divided by 2. And I'm just going to say about 2.6. And then I have 3 minus root 5 over 2, which is 0.77 divided by 2, right? And if I divide that about, so these are all approximations. We do not need exact values, it's just ballpark is good enough. About 0.4 is good enough. So when I do my first derivative test, I have the infinite domain over here from negative infinity to positive infinity. I have to line up my partitions. Negative 1 and then 0.4, which is 3 minus root 5 over 2. And then I have a positive 5. Positive 1. And then I have the last partition at 3 plus root 5 over 2. So these are my partitions, and now it's time to... What happened?
Partitions are where the function is continuous. That's what I mean to say. At those points, is the function discontinuous?
Function is discontinuous at negative 1 and 1 because there are vertical asymptotes there. But the other points should be min or max, so it's going to be continuous there. So now, if I take a look at my first derivative, remember I factored out negative 2. We do have a denominator, which is squared, and this was x squared minus 3x plus 1. Was that it?
Yes.
Yep. All right, good. All right, so now I need to pick 5. I need to pick 5 test points. Well, negative 2 0. Those are the easy ones. 1/2. And this is, and then 2, and then 3. There we go. And the reason is because the first square root is about 0.4, 0.3 something. So that's less than 0.4, and 0.4 is less than 1/2. So that's why we pick 1/2 there. And then 3 plus root 5 is about 2.6. So you can put 2 and 3 on each of the sides. And now we have to do those 5 calculations in the first derivative. But luckily, we already have negative divided by a positive times x squared minus 3x plus 1. So what we have is actually negative times the parenthesis. So we just need to compute these values in that parenthesis, and then if it comes out positive, the whole thing is negative. If it comes out negative, the whole thing is positive. So the first value we are computing is negative 2. So I have negative, and then negative 2 squared is 4, plus 6, plus 1. The whole thing is less than 0. So we have a decrease on the first derivative computed at 0. It's going to be negative 0 minus 0 plus 1, also decreasing. Now we calculate at 1/2. Negative times a quarter minus 3/2 plus 1. Well, that's going to be a negative quarter, so altogether positive quarter, bigger than 0, increase. If you're not following my fast calculations, then you just, you'll be using calculator later. Calculate at 2. So that's 4 minus 6 plus 1. So that's going to be negative 4 plus 6 plus 1. No, 4 minus 6 plus 1. That's negative 1. So the whole thing is 1. So it's larger than 0. So we have another increase. And finally, f prime of 3. Negative. I have 3 squared. That's a 9 minus 9 plus 1. 9 minus 9 plus 1. The whole thing will be negative 1, less than 0. And I have a decrease. So what we found is that there is a minimum at the negative root 5 and a maximum at the positive root 5. Second derivative test. Well, first find second derivative. So first derivative f prime is equal to negative 2 x squared minus 3x plus 1 divided by x squared minus 1, everything squared. That's the first derivative. So now we find the second derivative. I'm going to put this into the machine over here. To get this,
I use chain rule in addition to quotient rule.
yeah, that's exactly what has to happen. Plus 6x minus 3. Now that's all from the previous chapter. X squared minus 1 cubed. There we go. Set this equal to 0. The 0 will kill all of these, right? And we will just have to focus on 2x cubed minus 9x squared plus 6x minus 3 equal to 0. That's the only thing that we need to solve. Now again, these are all not so pleasant calculations. And they gave us x that we will have to simplify. Cube root of 5 plus 5 to the 2/3 plus 3 divided by 2. Now, So now I would like to know, well, we know it, at least we know it's positive, but I would like to know what is the approximate value for this monstrosity. So 5 raised to...
Well, I can't calculate cube roots on my calculator.
You raise it to 1/3.
Oh.
Plus 5, raise it to 2/3. Plus 3. Divided by 2. So about 3.8. About 3.8. We still have two vertical asymptotes, x equals plus minus 1 for our partition. On the second derivative test, we have to partition. So we have our infinite domain, negative infinity to positive infinity, and we have to make these three partitions. Partition number 1 for negative 1, partition number 2 for positive 1, and partition number 3 at about 3.8. To pick our test values now, we pick 4 numbers. We pick negative 2, we pick 0, we pick 2, and we pick whatever, 5. We can pick 4. And then we have to compute all of this in the second derivative. So we'll start with, now observe that the denominator, guys, is cubed. So denominator will be preserving the value of the sign because it's now 3, not the 2, like last time. So we actually have to compute. No shortcut here. The only one you can ignore is the 2. That's the only one you can ignore. The rest you have to compute. So it's 2 negative 2 cubed minus 9 negative 2 squared plus 6 times negative 2 minus 3 divided by everything cubed. Yes. Now you can actually ignore the cube because whatever is the value, positive or negative, the cube will preserve it. So you can actually drop the cube in denominator. So I have negative 8, negative 16, positive 4, negative 36, negative 12, negative 3. So the top is negative. Now denominator, I have a 4 minus the denominator is positive. So the whole thing is less than 0, concave down. And now I replace all of these negative 2's. I replace all of the negative 2's with 0's. So copy. I replace all negative 2's with 0's. And I just actually need to look at these last. So the whole thing is just negative 3 over negative 1, which is positive, and you have concave up. Okay, now we replace all negative 2's with positive 2's. And compute. So now that's 2 cubed is 8 times 2 is 16 minus 36 plus 12 minus 3 divided by positive number. That's negative 20, negative 8, negative 5, negative over positive is less than 0, concave down. And now we plug in the same with 5. Replace all the negative 2's in this case with the positive 5. The bottom is positive. It's 24 cubed, that's positive. 125 times 2 is 250. Minus 9 times 25. Okay. So 9 times 25 is 225.
So I lose 25.
Because 25 times 10 is 250, and then you take one of the 25s away, you get 225. Plus 30 minus 3. So that's 25 plus 30, so this is going to be positive over positive, larger than 0. Concave up. We're done with the first derivative test, done with the second derivative test, so we can graph. Now graph is going to go in the middle because we have a lot of these features over here. I'll start with asymptotes. I have 2 vertical asymptotes, one at negative 1 and one at positive 1. I have a horizontal asymptote at 0. So that's my y equals 0. And the red ones are x minus negative 1 and x is positive 1. Vertical asymptotes. Now I have x-intercepts, y-intercept. Let's go all the way up there. An hour ago. 0, 3, and 1.5, 0. 1.5, 0. And a 3. Yeah. Terrible, but such is life. These are the values. Now I also have .6, 0.4, 3.8. 2.6, 0.4, 3.8, right? 3.8? That's what I calculated? 3.8, okay, good.
It was 3.8 for the second derivative test.
Yeah, that's inflection. So these are my critical numbers, and this is my inflection number. So now I have to calculate the y values, because those points need to be plugged on a graph as well. Now, what was my graph? I mean, no graph, the function. What was it? 2x minus 3 over x squared minus 1. Okay, so let's compute vars function of open parenthesis 2.6. So it's about 0.4. So 2.6, 0.4. That's the first one. 2.6. And what was that? Min or max? Min, right? For min, we have this. Now at 0.4, we have, no, this is supposed to be a max rise, because it has to follow, it has to go through this point here, and the other one, 0.4, should be a min. Let's go find it.
My mistake, I have to lose track of the process here.
Second entry of 0.4, 2.6. So 0.4 and 2.6. All right, good. Nice. All right, we got it.
I'm sorry, I lost track of the problem.
Well, we just need to graph it now. He has to follow the asymptote, go through x-intercept, hit the maximum, and fall down to x-asymptote to follow to infinity, to follow the y-asymptote. Prior to -1 asymptote, we have concave down and decreasing. Concave down and decreasing is this. The only two you can draw is one on top and one on the bottom. Well, one on top is increasing, the one on the bottom is decreasing. So that's why we do the first derivative test. We know it's the one on the bottom. And the only thing that it's left for us to do is the middle part, right? Now, for the middle part, between -1 and 1, we better have concave up. Yep, -1 to 1 is concave up. So what I need to do is I need to follow. So this part is bad over here because the graph is outside of the range over here. But you have to go down into the minimum and bend back to follow the asymptote. And then through this one you go up and follow the other asymptote. And that's the graph. Now we're going to go to Desmos and make sure that I can still calculate basic stuff. 2x minus 3 divided by x squared minus 1. Hey, what do you know? Perfect. Oh, if I push the button. What happened? I mean, what else would you do with your time? This is perfect.
The rest of the test will be
Yeah. Where it's like, throw him under the bus. It's like, that's what friends are for.
So we have an hour and 15 minutes
Okay.
for tomorrow's test. Right?
Hour 20, yeah.
Hour 20. So
What was the point?
Is the final 2 hours long?
Yes.
So it's probably 20 questions.
No, it's 13 to 15 questions on the final, depending on the spice level and stuff.
Oh, the finals is fun.
My final was 5 questions in 4 hours.
That's good.
Yeah, you just need to solve 3 and that's all. 3 out of 5. I mean, you pass
I
the
think
second part.
the
Fine.
is like,
You don't pass the final, you pass the second part. Fine.
I think it's the difference like 5 questions, 2 hours. Like, that is a really long question with a lot of chances.
I said 5 questions, 4 hours.
Yeah, even worse. It's like how long are the questions and how many mistakes can I make?
Like the Ferris wheel would be a good one. Ferris wheel problem I mentioned. And that will definitely be one of the good ones. Sometimes professors go, oh, it's a cool problem, no clue how to solve it, so we'll put this one on and someone will do it. And then they know.
Excuse me, can I say? You could be able to schedule office hours tomorrow?
Yeah, we'll see after class. Okay. Any other questions, concerns?
Nothing I can think of at the moment. Give me a moment. I don't believe I have any other problems.
Yes.
Let's do a real quick reflection on the chain rule.
The what?
A reflection on the chain rule.
Okay, what's the problem for the chain? So that was in chapter 3, right?
Yeah, I know.
So anything that it's like the inside of a function gets copied first and then you differentiate it in a product later. So we have
Yeah, that's what
the derivative of, I don't know, cube root, since it's so fun. Cube root of 4 sine x, huh? That looks perfect. So we're going to rewrite this.
I think the problem we just had could be used as an example for this, if we don't mind.
Well, it's too long. That's the problem. 4 sine x to the 1/3. So in the chain rule, you kick the exponent downstairs, you keep the guts as is, you subtract 1, so it's going to be negative 2/3, and then you take the derivative of the inside, which would be 4 cosine x. 4 cosine x. So the total over here would be 4 cosine x divided by 3 times 4 sine x to the positive 2/3. That's the chain rule. I think it was what, 3.7? I think it was 3.7.
Oh, it is.
Now the chain rule will be used a lot, obviously. everywhere, including Calc2, differential equations. So you need to know chain rule at all times if you are continuing.
You need to know how to organize breaking the function down into separate parts. You said they go about it as if you were solving the problem, plugging in a value for x.
Yeah, if you are. So what would you first calculate, and then what would you calculate next? So that's how you know your layers.
I do that in reverse.
Yeah.
And also to get rid of the square of the radical, change it into a fraction, right?
Yeah. So anything else?
I have one, but I don't know because
What is the acceptable test?
that one, that's the same one. I don't think they're the same one.
I said
I can get that. You literally, so it says let me use basically your area is x times x, or x times h, and you solve for it.
Yes, I swear to God, it's not in. It's not.
That's
in
his
that
fifth number.
It's not in there.
Right
there.
Now
Look, it's. I do not see this.
I'll tell you why though, but because they want you to.
plug in. Once you plug into this one, because from here you're gonna get over there 390 over 330 over. So you get 30 over x. So this is the equation.
Okay, but here's actually the problem. So they good. I got so when I plugged in, I got something like it says it was 4h plus. I don't know where to get the
I'm so hungry that it actually hurts. I just can't do this anymore.
Like me neither.
I'm so hungry.
Yes. Yes. Yes, that's the word. How fast is the volume changing when the radius is blah blah, or how fast is the area changing when the length of the side is blah blah. How fast the distance between two airplanes is decreasing when one airplane is 500 miles away.
Excuse me, Professor.
So that's how you get you always get a question that asks for rate of change of something. That's the delayed rate. An optimization problem is always asking you to maximize or minimize something. What is the shortest distance? Well, you're looking for minimum distance, right? What is the largest something? Well, you're looking for maximum in that case. So you will always recognize the two word problems apart by the words they use. Right? One is using rates in its wording. The other one is using words that stand for minimum and maximum. They will say approximate the change, so you will know. Yes. So the wording in the word problem says approximate the change if radius grows or side grows or length grows. And then they give you two values. The beginning, what I call old and new, from old to new. So new minus old to get the delta x or delta r or delta whatever. You go new minus old.
It's because I'm just confusing the differential.
Yeah.
So the differential one is asking for how much the volume is changing.
Yes.
Over the rate.
The other one is asking you to calculate the rate of change. So it's different.